Let us next start chapter 2. You can see that the title itself says what we are going to do here. First order equations for which exact solutions are obtainable. We have already seen that not every differential equation can be expected to have exact solutions. We discussed about it in the first chapter itself. However, some special types of first order equations do have exact solutions, and there are definite methods that can be followed to find these solutions. That's what we are going to do in this chapter. We are mainly going to consider exact equations, separable equations, and linear equations. Each one of these types of equations has a definite procedure for finding the exact solution that it has. Besides these three, we are also going to see some very special types of, again, some other equations for which also exact solutions can be obtained. However, they are so special that they are not classified like this exact equation, separable equation. They are much more special than these three types. Okay, so it starts with exact differential equations and integrating factors. We will see what integrating factors are. Using them, we can find these exact solutions to this first type of equations, exact differential equations. Now, before we get to the definition of exact equations, we are going to first of all see two standard forms in which we can have a first order differential equation. One of them, of course, is our familiar form, this, where on one side you have dy dx, on the other side you have some function of x and y. So we have already seen this. There is another form in which we express the differential equation which does not have the derivative, but it has the differentials dx and dy, and accordingly this second form is called differential form. There is a technical term in mathematics whose name itself is differential form. It's not exactly that, okay. This form of equation is being called an equation in differential form because it has these differentials. And if you want to recall what differentials are, dx usually is treated as a small increment in x. But if that sounds a little strange, you can also consider dx as a variable. Okay, just like x is a variable, dx is another variable. It's a different matter that in most cases it is interpreted as a small increment, infinitesimally small increment in x. And what is dy? Because in most of our things where we will have x and y is a function of x. So the definition of dy is actually given in terms of dx, like this. Dy is another variable, and the meaning of dy is this. This equation is a source of confusion, really. It's very tempting to cancel these dx's and have dy. However, you should not, of course, do that because this is not a ratio of dy and dx. The source of confusion really is this notation itself. In place of this, say if instead of writing y and x simply like this, if you write y as a function of x, say y is equal to f of x, then dx is a variable and the definition of dy in that other notation looks like this. Okay, so dy, the meaning of dy is the derivative of f with respect to x at that point x times dx. So you see that dy depends on the derivative of the function and additionally that other variable dx as well. This is what dy means. But because of this notation, that confusion arises. But anyway, so we have dx and dy. However, the asymmetry between the variables x and y that we usually have in this type of situations where x is always the independent variable and y is always the dependent variable is not present here. This expression is symmetric with respect to x and y. So it does not really give us any indication of which of the two variables we should treat as independent and which one will be dependent. You can actually, when considering this type of equation, interpret y as the independent variable and x as a function of y. That is possible. However, we will never do that. Even when the equation is in this form, in differential form, we will treat x as independent variable and y as the dependent variable. And if our first order equation is given in this form or this form, we can transform it into the other form like this. Say you consider this equation dy dx equals x square plus y square divided by x minus y. Because you have x minus y in the denominator, the domain in which this differential equation is defined, there you should not have any point where the x and y coordinates are equal, because otherwise you will have zero denominator. So we push those things in the background. Okay, that's already there in the background. So we just assume that there is no problem in considering x minus y in the denominator. We instead focus on the form of the differential equation itself. So it is in this differential, not in the differential form, but in the derivative form. Now we want to turn this into this form. So what do? We first multiply. Let's just do it systematically. Okay, for once. Usually what we do, we really, while doing this type of calculations, we really treat dx as if it's in the denominator and we then bring dx to that side. Do not think like that. Actually, that's not what is happening. Multiply both sides by the variable dx. So then the left hand side becomes dy dx times dx. And the meaning of that is dy that we saw here. And that is why we write dy here. And the right hand side is this. And then of course you can multiply both sides by x minus y. So that way you get this. And then you bring this over to this side. X minus y becomes y minus x. So that way you get this equation, which is in this form. So you can see that the function m of x comma y in this case is x square plus y square. And the n function is y minus x. Just like we can turn this form into this form, we can do the opposite also, like this. So this second equation is in the differential form, in the second form. Sin x plus y times dx plus x plus 3y times dy is equal to 0. So we first bring that over to this side. So it becomes minus of this. And then we write what dy means. Dy means dy dx times dx, where we should not forget that this is not a ratio. This is the derivative of y with respect to x. It's a function of x again. Now the variable dx that you have on both sides is not equal to 0. Even when we interpret this dx as a small increment in x, it is infinitesimally small, but it is never 0. So we can cancel it from both sides. And then we of course also divide by x plus 3y with the assumption that x plus 3y is not equal to 0. And that way we get dy dx equals this. So the original equation which is in this form has been transformed into this form. Okay, so we will at times work with one form or the other form interchangeably, whichever is convenient for us. Next we come to the definition of exact differential equations. But before we define the actual this type of equations, we are going to need another definition. So let's see this definition. Suppose that capital F is a function from some set D into R. So capital F is a real valued function. So its outputs are real numbers, where D is a subset of R2. This tells us that capital F is a function of two variables, 2. And D is a domain. You recall what the definition of a domain is. It's a subset of R2, a subset of the plane which is both open and connected. That is its topology. Additionally, let the partial derivatives of this function, because it's a function of two variables x and y, so we can calculate the partial derivatives of f with respect to each one of them. Say these partial derivatives are continuous in D. This actually has two conditions in it. The partial derivatives first of all have to be defined in D, which means that capital F must be partially differentiable with respect to both these variables at every point of D. And then these functions, so that just tells us that these two functions are defined in D, everywhere in D. And additionally, these two functions have to be continuous everywhere in D. Say that is the requirement, that is the condition. With these things, we then define the total differential of f, of our function f, and we denote it by df by this formula, by this rule. The total differential of f is the partial derivative of f with respect to x times the differential dx of that x. So it is that differential that we previously got, plus the partial derivative of f with respect to y times the differential of y dy. So if you treat these differentials dx and dy as variables, which actually they are, you observe and understand that this total differential is actually a function of four variables, x, y, because you see, say you want to calculate the value of the total differential at some point in D, say at x comma y, then you need not just the values of x and y, because you would need those values here in these partial derivatives. So you have those values. Additionally, you are going to need dx and dy also. So it's a function of four variables, x, y, dx and dy. Okay, so that is the notion of total differential. Let's see one example. This is one example, and the function here has the entire plane R2 as its domain. See, we have two uses of the word domain here. One of them is function domain, which we already know. Whenever you have a function, you have a domain. It is the set of all inputs, where inputs come from. And the other meaning of the word domain is an open connected set. So is R2 open and connected? Yes, it is open and connected as a subspace of itself, or as a subset of itself. So okay, so f has a domain as its domain. What next? So the rule for f is this: at any point x comma y, this is xy square plus 2x cube y. So it's a polynomial function in x and y, in two variables. So at any point x comma y in our domain, we can calculate the partial derivatives. When differentiating partially with respect to x, you have to treat y as constant. You already know these things from calculus. So this one will give you y square, and this one will become 6x square, so 6x square y. And when differentiating with respect to y, you treat x as constant. So from the first term, you are going to get 2xy. And from the second term, because here you just have y, so y will vanish and you will have 2x cube. And that is why. Oh, but before we consider the total differential, you should not forget that other condition. Are these partial derivatives defined at every point in this domain? Yes, because they are again polynomials. And additionally, they are continuous as well throughout R2, again because they are polynomials. Multivariate polynomial, that does not matter. These are always continuous. So we can consider the total differential, which will be this del f del x times dx plus del f del y times dy. And this is also a function again of 4 variables x, y, dx and dy, but it's defined for all x comma y in our domain, which is R2. Alright. Now with the help of this total differential, this notion, we are next going to actually define exact differential equations. Okay, so this is the definition of an exact differential equation. But before we get to the equation part, let us first see what an exact differential is. Say you have an expression like this. Note carefully, an expression, not an equation. Okay, there is no equality sign or anything, just an expression which is that familiar expression. Okay, m dx plus m dy. Now, such an expression will be called an exact differential if there exists an exact differential in some domain D. Where it is being considered as an exact differential, that also matters. There is a subset of the plane in which this expression will be called an exact differential if there exists a function f whose domain is that domain D and which is real value, such that for this f we can calculate the exact differential df. So that means that f satisfies all those conditions. The two partial derivatives exist in D, they are continuous in D, such that the total differential of f equals this expression for all x comma y belonging to D. If this happens, if such an f exists for which this happens, then we will say that this expression is an exact differential in that domain D. In other words, going back to what this df actually is, it is del f del x dx plus del f del y dy. This condition, having this condition means having this partial derivative with respect to x being equal to m and the one with respect to y being equal to n for all x comma y belonging to D. And now, if this expression is an exact differential in some domain, that part is not being talked about again. Okay, so that is there in the background. Then this equation, finally we come to the equation. That expression equal to 0 will be an equation that is called an exact differential equation. Okay, so this is the meaning of exact differential equation. To put things simply, such an equation will be exact if there exists the function f such that df is equal to this left hand side. Let us see one example. In this second example, say we have this differential equation y square dx plus 2xy dy equal to 0. So what the author suggests is this function capital F from R2 to R, and the definition of capital F is this: at x comma y its value is xy square. Obviously the partial derivatives exist. Differentiating partially with respect to x you get y square, and differentiating partially with respect to y you get 2xy because it's xy square, y square gives us 2y. So these functions, these partial derivatives exist throughout the plane, and because these are polynomials in x and y, so they are also continuous throughout the plane. That means the total differential of capital F exists, and it is actually nothing but this left hand side. Del f del x is y square and del f del y is 2xy, that is y. And that is why this left hand side expression is an exact differential in this domain R2, which makes this equation an exact differential equation in R2. However, the author then next says that instead of that equation, if one considers this y dx plus 2x dy equal to 0, where you may notice that one y from each term has been lifted. Here we have y square, here we just have y. Here we have 2xy, here we have 2x. this loses exactness. However, this raises two questions. The first question is, how do we know that this is exact? From the definition of exactness, it's nearly impossible to know that if a given expression is exact or not. How do you go about searching for this capital F? If you find an F accidentally, you will know that it's exact. Okay. However, if it does not exist, if the expression is not exact, for example, the author suggests that this is not exact, but why? Okay, so we don't really know why. And even if it is exact, we don't really know any method for finding one such F, which will give the exactness. So that means the definition alone is not sufficient for knowing or finding that F, knowing whether the F exists and finding if it exists. We need some kind of result, and that result is the next theorem, which however we won't see today, that we will see in the next video, and that will be all for today. So again, of course, tomorrow we have a new upload. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.